Lesson 23, demo. Today is all about practicing with our new derivative formulas to find derivatives of complex functions. Let's have a quick look at the strategy guide below. We begin with a pop quiz. Don't worry, it's not being graded. See how many of the derivative formulas you remember as you fill in the second row of this table. So if you haven't filled that in just yet on your own, pause the video, just see what you can remember and fill them in. After you've done the best you can, come back and unpause the video. Okay, so go ahead and pause the video here and check your answers. And then we'll continue on through our strategy guide. We only have specific formulas for the derivative of a few functions. So if the function that we are looking at isn't exactly one of these, I don't know, what are there, 9 formulas in here? It's not exactly, well, maybe it's 10. 3, 6, 9, 10. If it's not exactly one of these 10 formulas, we don't have a way to do it unless we apply one of our like other fancy formulas like product rule or quotient rule or chain rule. But this is pretty much it. We have very few things we can differentiate in one step other than these 10 right here. So if you happen to have something that looks like a sum or a difference, then you use our very nice sum or difference derivative formulas. What are you looking for? You want the function to consist of multiple terms separated by pluses and or minuses, and you treat each term as its own derivative problem and then just add or subtract the derivatives at the end. Constant multiple rule. If you have a constant times a function, you can just copy that constant down and independently find the derivative of the function. You're looking for a constant by which the rest of the function is multiplied. You just find the derivative of the rest of the function and then multiply it by the constant. I copy it down first usually. Okay, product rule. We've seen this derivative many times. Does the function consist of two functions which are multiplied together? Use this rule to find the derivative of a product. Always remember the derivative of f times g is not f prime times g prime. An expression like cosine of x to the fourth is composition, not multiplication. This is cosine of stuff, not a product rule. And if there's a product inside part of the function, use a different rule before getting to the product rule. We'll see some examples. Okay, quotient rule, same deal. Remember, the quotient rule is not as simple as you might hope it would be. And let's see what the next page has in store. Chain rule, that's a big one. Derivative of f of g of x is f prime of g of x times g prime of x. What are we looking for? Well, hopefully one of the other above rules helped, but if not, maybe it's a chain rule. Does the function contain a simpler function? You can either identify the embedded and overriding, like the inner and outer functions, or you can do the Leibniz thing where you introduce a new variable and set it equal to the simpler function. And then we use a different version of this rule here. If there's a composition inside of a product or quotient, first you do the product or quotient rule, and then in the middle of that, you do your chain rule. Okay, so some examples here. What am I looking for, and what do I see in this one? I see a plus sign, and so that tells me that I should just do my basic sum rule, just the derivative of these two separate things, independent with a plus sign in the middle. 3x to the fifth, what do I notice? There's a 3, that's a constant multiple, so I can just treat the 3 separately. I just put it in the front, and then take the derivative of x to the fifth, and then multiply them at the end. X to the fifth times sine of x, that is a product of two different functions of x, so we use the product rule. The answer is here. Likewise, this is a quotient. Got to use the quotient rule. This is a composition, but this is a different composition, so be really clear on the difference between these two. This is sine of stuff. This is some stuff to the fifth power. Sine of stuff becomes cosine of stuff times the derivative of the stuff, but stuff to the fifth becomes 5 stuff to the fourth times the derivative of the stuff. Okay, this is first and foremost a quotient rule, but in the middle of doing the derivative of the bottom, you're going to recognize there is a product rule down there. So there is the answer. This is a product rule, but in doing the derivative of the second, you're going to find a chain rule, sine of stuff, just like we did sine of stuff up here. This is ln of stuff. That's a chain rule. But when you get to take the derivative of the stuff, you have to use the product rule. That is a product in there, and so its derivative goes separate after you do the 1 over the stuff part. Okay, so let's put these into practice here, starting with A. We're finding the derivative of root 2 to the x times ln of x. So here we go, g prime of x equals. Okay, what I see is a number to some stuff. I have a formula for the derivative of a to the x. A in this case is square root of 2. So we apply that basic formula. It would normally be square root of 2 to the x, but it's stuff up here instead. So we copy that one time. Times, still doing the a to the x rule, it's always times ln of a, ln of square root of 2. Now the chain rule comes and says take the derivative of the stuff. And the derivative of x ln of x requires a product rule. And so the product says first times derivative of the second, derivative of ln of x is 1 over x, plus the second times the derivative of the first, derivative of x is 1. That's it. Okay, next one, derivative of e to the cosine of ln of x squared plus 1. First thing I see is e to the stuff. I'm comfortable with the e to the stuff rule. It just becomes e to the stuff times the derivative of the stuff. So there's my stuff, and its derivative needs to go in here. And so the derivative of cosine of stuff is negative sine of the stuff. Times the derivative of the new stuff. And the new stuff is now ln of x squared plus 1, and that derivative is going to go right here. And this is yet one final chain rule. Ln of stuff becomes 1 over the stuff. So 1 over x squared plus 1 times the derivative of the stuff. And the final stuff is this x squared plus 1, and its derivative, we're going to squeeze right in there. And the derivative of x squared plus 1 is simply 2x. Okay, group activities, a little bit unusual today. You're gonna, it's essentially just starting your homework, so you're gonna get as far as you can during these activities. You're gonna be doing 1 through 73 odd from the review exercises at the end of chapter 3 in your book. It is copied on the next page, so regardless of which edition of the book you're using, don't use your book, use the stuff that's photocopied on the next page. You can skip any problems that have any of these letters, A, B, C, or K. Those are all treated as constants. You can do them, you have the tools to do them, but we haven't really done too many things where we have constant letters sitting inside of our derivative problems. All right, 1 to 73, I think that's 37 problems altogether. You don't need to do 37, but more is probably better. If you only do 20, that's okay. 20 is the minimum to get full credit for this homework. But if you can do more than 20 and maybe even all 37, that would be awesome. But if you only do 20, do not do the first 20. Skip around, look through. So the toughest problems are typically at the end in the homework. So don't just do the first 20 that you see. You can check your answers with the answer key. There's both an unsimplified version of the answer key. You can stop there once your answer matches the unsimplified version. But if you want to make your answer match the key in the back of the book, there's also a simplified version of each of the answers. Also, you can find solutions, not just answers to all these problems in the binders in the studio. I'm also going to make a video for all of the odd problems right now. So you can check out the video for the activities if you get stuck on any of them.